So welcome back. Today is the 27th of October, Friday. This is CSC241, computer architecture, better known as hardware. Computer hardware. And what you're looking at is the Module 4 Study Guide Addendum. And the Module 4 Study Guide Addendum is chock full of important and relevant information. And I might add, it's also positioned in the references folder. What do we know about the references folder with regard to our criteria for study before you attempt the module assessment? Can anybody tell me what we've explained previously about anything that's in that reference folder? What's our word of caution to you? Is that for light reference when you happen to have the time? Or is it something that you should thoroughly scour and commit to memory?
The latter.
Yeah, going forward in the class, this is especially true. If it's in the references folder, you really need to take the time to get into it because the assessment items are going to be tapping that kind of thing. And in our addendum, we basically take some quality time to call out in a written context, right? So this class is multimodal. We walk through some things in person on the screen and then reference the website, and I explain some stuff out of the study guide. And then this is basically text-based information. What we know is that some students learn better by video and live web and that kind of thing, media-based, video and audio. Other students are strong when it comes to learning from written format, right? So we want you to take the time. The reason I'm sharing this with you is it matters not to me whether the information is video and audio based or it is textual based in a PDF reference. If it's in references folder, it's fair game for the assessment, okay? Does everybody understand that? So if there's a link with a YouTube, you got to watch it. If there's stuff that's been paper or you got to read it, it's digital paper, then you got to read it. And this information is very helpful. The idea of a collector and a base and an emitter, it's talking about how that becomes the switch, that becomes the transistor, that becomes the logic gate, okay? And then there's additional information. So in our updated version of study guides recently, we gave you information about the arrow, up pointing arrow and down pointing arrow as a symbol, right? Yeah. And then now we have another one. A circle with a dot is XNOR. So again, that information is important. Now, if you have a exclamation point in front of the caret symbol, that's the same as a not in front of the XOR. So this was the symbol for XOR. This is the symbol for not. The two together is one way of representing the logic gate we know as XNOR. Everybody got that? Just wanted to spend a little time to walk through that. So we were talking about memory registers. And we said that one thing we need you to know is the logic statement for DFF and to be able to distinguish it from the logical statement that represents a memory register. So it is this out equals out cycle or iteration that requires the refresh of electricity. Right? A flip-flop by itself, on its own, apart from other logic gates, that it's not the same dynamic. When you get to this point and you're cycling, okay, what comes out of here is what came out of here last minute, last hour, last day. That's the power element. That's where the electric power has to be applied for random access. Now, I do want to take a little longer just a moment to explain again, random means this memory. Okay, it requires power, but the other thing about this memory that's special is that it's very flexible. That data and instructions can be randomly placed in different memory address ranges. So memory is identified by an address. In the same way that the network interface on your computer or laptop or device or smartphone can be identified by the network interface, a memory location is designated by the address. And as memory is needed for random purposes or incidental purposes, address ranges can be allocated so that we can store temporarily instructions and data. We have looked at the von Neumann model of the computer yet, right? Does everybody remember von Neumann? John von Neumann? Did we not talk about John von Neumann?
No, you have. Yeah. Maybe in another class.
Well, it's coming. And we'll get to it. And I want to say we go into it quite a bit more in the next module. But essentially, every computer has to have RAM. And the RAM stores statements, programming logic, instructions, right? How to compute the data. But it also stores the data upon which the programming statement operates. Now let's say that again. RAM is especially important because it's flexible, and as instructions are executed, the data upon which the execution is rendered, right, has yet another address location where it can be stored. So you have to have original data, you have to have computational instructions to work on that data, and you have to have workspace. We've often said in many of our classes that RAM is like the workbench of a craftsman's workshop. If you were a craftsman and you were in a workshop, your working space, your workbench would be like the RAM of a computer. The bins and shelves that store your materials and your tools would be like the hard disk. And the craftsman, him or herself, would be the CPU. Does everybody understand that analogy? Kind of, sort of? Maybe? Okay, if you had a leathersmith, if you had a blacksmith, if you had, doesn't matter, if you had a craftsman of any sort, if you had a tailor, where you store things, the materials, that's the hard drive. Where you're actually working on it is your table, your workbench or work table. We said RAM has three inputs: a data input, an address input, and a load bit. So the load bit is part of that mechanism for refresh. It's loading those ones and zeros. Now, not all stored memory works this way. So what we want to do at this point is take a moment to explain that when the power is turned off, if the content of that data is not written to a non-volatile, everybody, repite usted por favor, non-volatile. Non-volatile. There are other terms, but basically you have two kinds of memory: permanent memory, non-volatile memory. NVM memory is non-volatile memory. You'll see references to NVM. One common example of NVM that we're all familiar with are hard disks, right? So hard disks record that stuff, and then you have it. Any questions about persistent memory? Another word that we hear with memory used all the time is the word persistent. So persistent memory is non-volatile memory. If it's volatile memory, it means when the power is cut off, it's it disappears. Without power, it goes poof. It's like a vapor. Remember, volatile is like vapor, V for V. Any questions there? I want to talk about CPUs. Can we explore CPUs today? CPUs. So we talked about memory, and we talked about disks and persistent memory. If we're going to build a computer, one of the digital components we have to build is the arithmetic logic unit, or ALU. The arithmetic logic unit is the business end of a CPU. A CPU has three components: a controller, it has static memory, it has a memory register. So there's memory on the CPU itself, so that what the CPU is working on has it right in front, right there. And then, so there are very fast forms of memory. It's called it's static RAM, right? It's not dynamic RAM, it's static, it's wicked fast, very high performance, very expensive. But then we have the arithmetic logic unit. The first example of a CPU that was built was called the adder. And it was basically an adding machine, hence the term adder. That makes sense, doesn't it? You know, old-timey adding machines, you could, and then if you got a little further, adding machines also included other functions like subtraction, right? And multiplication and division. So what you have are some important things in that digital component that have to do with memory registers, where the least significant bit and the most significant bit are stored. And that's one of the essential components of how the adder operates. The idea of a least significant bit and a most significant bit is going to recur over and over and over again, especially when we start moving data across those digital components. Let me say that again. Whenever we're moving data into and out of digital components, we have to understand what the concept of most significant bit and least significant bit mean. So in this binary number, which of these values is the most significant? What would you guess?
The one.
The one. Okay. Could you say that the one represents more quantity than any of the other bits?
Yes.
So if we had the one inverted and we had a one here instead, and we had a bunch of zeros, if we have the one here and then we have zeros this way, the one here is worth what?
One.
Literally one. What's the one here worth?
16.
Well, let's see. 2, 4, 8, 16 is correct. Right? 1, 2, 4, 8, 16. We keep going. 32, 32. The leftmost bit is the most significant one. If you're adding two binary numbers together, here's something that becomes a problem. Let's say I add this number to this number. What does the CPU do? Well, it increments this by 1. Is that a problem? Can it use that same number and just increase it by 1 and then we're done? I guess what I'm asking is, in terms of what we have here, if I take that value, a 1 followed by 4 zeros, do I have to commit more memory or more resources to be able to perform the addition of 1 to that value? Well, I'm storing a 0 or I'm storing a 1, so I'm still using the same memory register, okay? So here I'm using 5 memory registers, and then if I increase this by adding 1, all I'm doing is flipping it so it's 1. So what about this right here? If I add 1 to this value instead, what happens?
It'll carry over to 1.
the 1 carries all the way down, and I have to flip the values. So the original 4 values here turn into what? 0, and then I have a new register that's required, and I have a 1 there. So there's a memory there. We have to basically add another register to the mix in order to be able to perform that calculation. Okay. Then we have special cases where we're adding negative numbers. Now in real math, you know that when you're adding a negative number, that's equivalent to what? Subtraction, right? So if I have a 4, a positive 4 on the number line, and I add a negative 2 to the positive 4, then I subtract. But isn't there a weird thing where if I'm like multiplying a negative number by multiplying with another negative number, does everybody know what I'm talking about here?
Yeah.
So if I take a negative 6 and a negative 4 and I multiply those two, do I have a negative answer?
No.
No, you get positive.
It turns positive, right? It flips. And we have this idea of a number line, but then we also have this concept of an absolute value. So a negative 4 times a negative 6, it flips the sign, and then we have the quantity of 24. Those are things we have to accommodate in a calculator. So if we want more than an adding machine, we have to be able to carry, and we have to be able to work with negatives. And this is where the full adder comes in. So the first adder that was built was called a half adder. It had memory registers, and it was able to do just so much. But then when they needed to do more things like negative calculations or big numbers, right? Carrying the places became, well, it just didn't work very well. So they added extra components, and a half adder became a full adder. And I just wanted you to understand that in the early days of digital components, they had it almost right, but then they got it right, okay? Now, would you believe that CPU manufacturers occasionally screw up in all of the billions? How many did we say was in a Intel i9? How many logic gates in an Intel i9? Does anybody remember our last class?
I think it
More
was
like
close to
billions?
60 billion or something like that.
That was huge, right? I mean, billions, I thought. Yeah, so the first computer CPUs were on the order of hundreds of thousands of logic gates, then millions, now billions. An i9 has billions of logic gates. Did you know that this design for a full adder, every now and then, a CPU manufacturer, oops, they make a mistake and they find out that for a certain mathematical operation, there's a bug and it's hard coded in the CPU and the CPU doesn't work right. I'm going to share a little story with you. Intel in the early days, can everybody still see my screen?
Yeah, we could still see.
Okay. So the Intel Pentium was a breakthrough. Because early CPUs, believe it or not, early CPUs were only 16 bits. Let me say that again. Early CPUs were 8 bits and then 16 bits. In fact, the 8086 processor was a 16-bit microprocessor. This is what went in the original IBM PC, personal computer. And when did the IBM PC actually come out? Okay. Does IBM, if it's IBM compatible, does IBM have any rivals? Does anybody else make computers?
No.
First computer was not, known as the Apple I, but then they came out with the Apple IIe. The Apple IIe was huge because it's what put Apple on the map. The first prototype was actually called the Apple I. And it was created in the garage of Steve Wozniak and Steve who?
Jobs.
Stephen Jobs. Stephen Jobs and Stephen Wozniak, right? Created the first Apple computers, and one of them that put them on the map was the IIe. Now the IIe was amazing because it was affordable to teachers. And teachers and professors started buying their own computers. And then all of a sudden, when did this happen? 1976, by the time the Apple IIe, when was the Apple IIe?
83.
83, right? So IBM came out with a personal computer. That's it right there. It worked with floppy drives, floppy disks, and it had 16 kilobytes of memory. Or you could have up to 256 kilobytes of memory. That's a quarter of a megabyte. You can't even take a picture on your phone for less memory that this thing had. Now, how much did it cost? A mainframe IBM computer could cost as much as $9 million back in 1981. In 2023 dollars, $9 million back in 1981 was like, I don't know, $50 million, okay? How much did it cost? The basic price tag for the IBM personal computer, which was manufactured in New York. It was manufactured in New York, as in the Empire State, right up the river from the Hudson River, from the Big Apple, right? That's where they made these things. And they made a huge announcement. And back then in 1981, if you had $1,565, you could be one of the first people to own a 16-bit CPU with 256 kilobytes of RAM, and you had floppy disks. You could boot it up and you could run your own spreadsheets or your own word processor. Instead of taking paper to a printer who had to manually set type to reproduce things, right? So just think about what kind of advances, or typewriters, right? You'd hand something to someone with a typewriter and they'd type it out on a typewriter. IBM made its first million creating typewriters. IBM wasn't a computer company at first. They were a typewriter company, and they had keyboards, okay? This is just a little trip down memory lane. Okay, so once you have a full adder and you have a 3-bit full adder, the one can be carried to the next column, you reach a tipping point, and that becomes what we know as the arithmetic logic unit. The arithmetic logic unit is the business end of a CPU. It's what actually performs the calculations that are stored in the memory register. Okay? And yes, 8-bit version, 16-bit version, 32-bit version. What are we dealing with now? So if you were an educator and you got on board with an Apple IIe, Apple started off and became the darling of educators. Why? Businessmen and women had more money. Teachers did not. So who owned which kind of computer? The business world owned IBM PCs. Teachers, if they wanted computers, they owned the Apple II series. And here's a picture of it, right? Everybody see this? That's the Apple II before the Apple IIe came out. The Apple IIe had a green screen. It had a green display. And the CPU was a 6502 processor, an 8-bit processor, right? Not a 16-bit processor. But basically, Motorola, has anyone ever heard of Motorola?
Yeah.
Motorola was one of the companies that decided they were going to support a new kind of chip for a new kind of computer. And the computer had 128K, which is actually less than the IBM PC, right? That could have up to 256K. But what was unique about it is this computer right here was the first of its kind to implement what we call a graphical user interface, a GUI. You had icons. And did you know that the Apple Macintosh, it was announced in the Super Bowl? So Apple computers had a huge ad that they paid millions of dollars to broadcast in the Super Bowl, right? In 1984, and it's actually a really interesting ad because they show a really lithe athlete coming out with a sledgehammer, and she destroys the IBM PC. Okay, because the IBM PC is nothing but characters. So what we know for computers now are input-output components, namely a display with icons we can click with a mouse. IBM wasn't the first to do this. Apple was. As soon as Apple did, IBM and Microsoft got sued because Apple said they stole their idea. Does anyone know what happened next after Apple won the lawsuit? Does anyone know what happened next after Apple won the lawsuit? They got sued. Apple didn't think of having icons on a screen you can interact with. There was another company you might know and heard of. This is really amazing. Has anyone ever heard of Xerox? Xerox, the copy machines, the photocopy machines.
Oh, yeah.
Yeah.
Xerox had a copy machine and they wanted to make it easier for their users, and they had a display that they had invented, and it was something that the users could work with based on what was the little icons, the little symbols that were on the display. This was something that Stephen Jobs and Steve Wozniak watched for the first time in a research laboratory at Xerox in Palo Alto, California. The Palo Alto Research Center of Xerox, the copier corporation, they invited Steve and Steve over to have a look at their technology. And Steve and Steve were amazed, and they saw the icons. And after Apple won millions of dollars from IBM and Microsoft for copying their idea, along comes Xerox, and they're like, not so fast. You're just as bad a thief. You stole that idea from us. You were walking through the Palo Alto Research Center, and this whole idea of what's going on. Now, why am I sharing this with you? The origins of computer hardware are fascinating, and it's the stuff of legends, and there are some milestones that it would be good for you to know about if you're coming out of an introductory to computer hardware class. Wouldn't you agree? So where do we get our graphical user interfaces that we use every day from? Xerox, the photocopy people. It was Apple who stole the idea when they made the first Mac, which was the first computer to have icons and mouse to move the thing, right? Actually, there were some Unix systems that had like peripherals where you could work stuff with a mouse, but that's another story for another time. They borrowed a lot of these concepts, put them in the Mac, and away you go. Any questions about our CPUs? We're not we're not talking about the fun stuff with CPUs, we're just giving you the basics. As a digital component, an arithmetic logic unit is the business end, it's the one that actually does the calculations. Now, we use the internet. We connect right now in Zoom, and we're sharing things right now in Zoom. And that information is flowing back and forth in millions of ones and zeros as we speak. So as I'm delivering this lesson to you right now, there are ones and zeros that are flowing between my screen and your screen, and there's audio overlaid on that. And this is all happening in real time. And you have the perception that it's moving video because there are 24 to 30 separate, and then in some display screens, it could be 60 or 90 or 144. There's a refresh rate. So the number of pictures that happen in any given second is so fast that you can't see that it's just individual pictures. But the truth is that there's an electron gun that's lighting up phosphor dots on this screen back and forth, and it happens down the screen so fast that it happens 30 times a second. In a movie theater, the pictures in a movie theater, an old-timey movie theater, were rigged 24 pictures in a second. So when the movie projector was rolling, 24 pictures would appear on the movie screen, and your eyes would think that that image is moving. But it's not. There are slight differences between each of the pictures, and that's what's going on.
Movies are still shot.
Say again?
Movies are still shot at 24 frames.
Movies are still shot at 24 frames. Yes, there's a classic. That's a kind of a time-honored standard. You can shoot a movie at much higher frame rates, and then when you want to slow it down, you can basically play back at 30 frames a second and capture at 120 and it's quarter speed and all that. That's how people do slow-mo.
Yeah, slow-mo usually very fast when you slow it on the keys.
Yeah,
It doesn't just look like a slow down video.
that's correct. It doesn't just look like a slow-down video. If it's played back at 30 frames a second, to you, it looks like it's smooth, but it's not. That's an excellent point. The thing that I'm trying to stress here is that a digital signal processor and a universal asynchronous receiver transmitter, a DSP and a UART, those are things that move the media, the ones and zeros. In particular, we have things like auto-tune and MP3 players, we have telephones, modems, fax machines, all of that. These are the digital components that move ones and zeros. When you have ones and zeros in motion, these are the digital components that are responsible for that. DSPs and UARTs, right, combined created a device known as a modem, which was short for modulator demodulator. And this was something that actually worked on a phone line. Now, it pains me to say this, but when I was your age as a student, and I'm just asking if any of you remember grandparents or great-grandparents, did they or did they not have a telephone that was bolted to the wall and there was a wire connected? Do any of you remember visiting older relatives, and if you went into their homes and they had old school stuff, that they still had a telephone that was wired and it was stuck on the wall?
I think you're talking about when I'm there.
Okay.
They had
Anyone here? Did anyone, is there anyone in among our guests today? All right, so we have 10, 12 students in the mix. Does everybody know what I'm talking about?
Yeah.
So we have this thing, we're not going to get into it a lot. Plain old telephone service, right? The public switched telephone network, or PSTN, plain old telephone system, right? these were analog telephones. And basically, have you seen older movies where people are working with stuff like this?
Yeah.
Okay, so there was a wire that connected it. The modem would take the voice line and it would squeal, and the squeals represented ones and zeros. So when it was done real fast, this is what it sounded like. There. Everybody hear that? All right, so basically the squeal sounded like so much noise, but the squeal carried ones and zeros. That's the whole point of modems. So modem, the common name modem was a short version of modem modulator demodulator, and you used phone lines to get on the information superhighway. This was back in the 80s and 90s. This was the internet before. This was the internet before everybody knew about the internet. Okay, so it made this warbling and squealing sound, and you were very fortunate. You were somebody that had money and resources, because you could take your computer and you could connect it to a phone line, and you could run 56,000 signals, or baud, which was the equivalent of 56,000 ones and zeros. In other words, you could work with 56 kilobytes of information each second. 56 kilobytes each second. Now, when we download stuff and we're downloading Netflix, what's the size of the average Netflix movie? Yeah. Average size, high def Netflix movie. In bytes. So it says the average size of a Netflix movie, depending on whether or not it's high definition or it's standard resolution, is between 317 megabytes and 7.5 gigabytes. All right, so let's do some quick math and then we're done for the day. And then we'll break for the weekend. 56,000, right? Everybody with me? 56,000 warbles make 56,000 bits. Bits. 56,000 bits. I have to divide by 8. That means I'm getting 7 kilobytes per second. 56,000 bits on a modem is 56,000 ones and zeros each second, and you have to divide by 8 to get bytes. And that's 7,000 bytes, which is 7 kilobytes. If I divide by 1024, that's 6.8 kilobytes per second. I'm going to store that value, okay? I'm going to add that to here. Remember kilobytes, we're working in kilobytes, okay? Now, 7.5 gigabytes, how many megabytes is that? I have to multiply by 1028. 1024, I'm sorry, 1024. That's 7,987.2 megabytes. I'm sorry, what? Okay, 7.8 gigs, 7.5 gigs. Thank you, times 1024, good catch. That equals 7,680 megabytes, not bits. Now, How many kilobytes is that? What do I multiply by? Another 1024. So I get 7,864,320 kilobytes. I stored how many kilobytes in the other one? 7 kilobytes. 7,000 bytes makes 7 kilobytes. So what I'm going to do is I'm going to clear my memory actually. I'm going to store this value. And then I'm going to take 7 kilobytes and divide it by memory recall equals. Or let's do the reverse. Let's do the reverse. Memory recall divided by 7. It's 1,123,474 times larger, right? So when you look at internet connections that are capable of downloading a Netflix high definition, don't we have gigabit internet service now in some areas?
Yeah.
Yeah, so in theory, if you were very rich, you could have something that was even faster than consumer grade gigabit. You could buy, maybe Elon Musk has one, right? So he could download the whole thing in 1 second. The point is, I'm trying to make is, if you factor in the seconds, the number of seconds it takes to download at a gigabit per second, right? I can multiply that, I can do the math. Essentially what we're dealing with is many orders of magnitude faster, right? In 30 years, we have technology that's progressed where it's millions and millions of times faster and better and so on. And that gets back to Moore's law. So we said Moore's law was when what happens every 18 months to 2 years?
The number of transistors.
The transistors double, I think. Yeah.
Yeah, the number of transistors doubles, right? And we ask you if you could choose between getting $1 million or a penny that doubles every day for 30 days, which would you pick? Take the penny. If you do the math, you find out double it. By the time you get to 30, you're dealing with something much larger than $1 million, right? The $64,000 question is whether or not they can sustain Moore's law, because we're getting to the point where we're dealing with angstroms. Angstroms are the size of atoms. So we're dealing with very, very small logic gates now. When we have 1 billion logic gates that sit on a chip that's the size of your thumbnail, that's really, really small, right? And the other problem is we have heat. We have errors, we have all sorts of other challenges. If we have a single dust speck in that chip, it ruins the chip. One dust speck. So why don't we stop here? And I hope everyone has a good weekend. I'll be posting some things out there in Module 4 for your next assignment. I hope you've had a chance to get your personal computer ready. On Monday, we'll investigate how digital components present on your computer system. So we'll basically flip it and get hands-on. But we wanted to get through this much of our content review because we wanted to cover the essential digital components. Any thoughts, comments, observations before we clear for the day?
For the ALU, what is the logic?